What's up, everyone? Welcome to a very special edition of our AP Physics 1 seminar. I hope you're nice and cozy and bundled up because we've got some work to do. So we last left off talking about simple harmonic oscillators. And I will apologize in advance that I am left-handed and it'll take you a while to actually see what I am writing. But there you go, simple harmonic oscillators. These are objects that move back and forth at a regular rate in time. So for example, we have our pendulum, which we displace from some equilibrium line. We let it go, and it swings back and forth, converting gravitational potential energy to kinetic energy and back. We also had our spring system. This was a mass on the end of a spring. Again, we stretch that spring from its equilibrium point. We let go, and we now allow that spring system to convert elastic potential energy, or spring potential energy, into kinetic energy and back and forth. So each of these two systems is defined by a period. It is the time it takes for one complete cycle. So both of these objects essentially vary in time. They're one single object that changes its position with respect to time. So if we were to sort of extend, like if we had a whole row of pendulums, one after the other, and we all displace them just a little bit out of sync with each other and let them go, we would have each pendulum doing its own thing. So we can now have a function of space where we are in that row of pendulums to model that motion. And what we get out of that is wave motion. So wave motion varies in both time and space. So this wave is clearly changing its motion as a function of time, but depending where we are in the wave in space, we can actually see different things happening at the same times. So when we modeled our pendulums, our simple harmonic oscillators, we had some displacement. Here I'm going to write y to represent displacement from equilibrium. And we said that's equal to some maximum amplitude A, and then multiplied by a sine or cosine function with an argument of omega t. So based off this value of omega, we could see how rapidly this pendulum swings back and forth. Now we've got a whole row of pendulums, and we want to see a function of both space, where we are along that row of pendulums, and time. What time has elapsed since we started these things swinging. So again, the formula is going to be really similar, but with a pretty stark difference. Oh, that sounds like an oxymoron, huh? So we have A, our amplitude, multiplied by the sine of omega t. And now here's the tricky part, is we're going to subtract from that in the sine a kx. So what we have here is a part of the wave, omega t, that talks about what it's doing in time, and a part of the wave, kx, that talks about what this thing is doing in space. The little minus sign separating them between them tells us that the wave is moving to the right. So a wave, just like a particle, has a direction to its velocity. It can move to the right or the left or up or down. And the negative sign here tells us that the wave is moving to the right. If we had a plus sign here, that would indicate that the wave is moving to left. So keep an eye out for that. The sign that you see in front of the x term, the spatial term, is going to tell you which way this wave is going. All right, so now that we've talked about, how we can describe a wave, it really begs the question, what the heck is a wave? So a wave, really in general, is a disturbance from equilibrium. So you can go to the beach and you can look at the ocean waves coming in. Those waves represent ups and down displacements from a nice smooth water surface. If I have a sound wave, that wave is vibrating through the air and disturbing, the air molecules due to differences in pressure. If you go to a sporting event and do the wave, everyone is displaced and disturbed from their nice seated positions. So a wave is just a disturbance from equilibrium. Typically, this wave can repeat in a periodic fashion. You see the waves at the ocean, they come in one after another. But we can talk about, disturbances as pulses, just one single pump up and down of that wave as well. So this wave repeats in a periodic fashion. It's varying in both space and time, and due to that, it's actually very hard to draw a wave motion in a single go. So what we can do is we can sort of divide these up into spatial parts and time parts, trying to figure out what the wave is doing with each of its two space and time parts. So one way we can do that is with a snapshot representation. That's not what it is. Snapshot. A snapshot, essentially, you've watched this wave move back and forth. You take a picture of it, and now you have the wave trapped at a single point in time. And this is for the whole wave. So our graph is going to look like y on our y-axis. Move it up so you can actually see. And on our x-axis, we have x. So this is sort of where along the wave that we are actually looking. And if we're watching our ocean waves at the beach, we can see them go up and down and up and down. So now we've taken a picture of this wave. We can see maybe close to the shore, there's no displacement. As we get further away, the displacement is positive, and then it trends towards a negative displacement as we get further out, and so on and so on. So we've taken a single picture looking at what this wave is doing. That's represented by setting t equal to some constant, and then only looking at what's happening to the x part of our wave. So we look at this mathematically, we see that we have t is substituted in as some constant fixed value, could be 0, doesn't have to be, and then we're only looking at how the x part of the wave moves up and down. Likewise, if we wanted to look at what the wave is doing in time, we have to pick a single point on that wave. So I might pick this point here, and I want to see what that point is doing. So we call this a history graph. We're looking at what one point is doing in time as it moves. So a history graph is what a single location is doing in time. The graph for this is going to start out looking very similar. We've got our displacement y, but instead of looking at the whole wave in time, in space, we're looking at just one point on that wave in time. So where we set t equal constant over here, here we're going to set x equal to a constant, and that constant represents how far along the wave we're looking. So this might look at, if we're looking at this point here, this one starts displaced up in the positive direction, and it might go up and down from there as it moves. So now we're looking at just this single point on a wave as it bobs up and down in time. So these are our two ways to look at a wave. We can freeze it in time as a snapshot, or we can look at one single point and see what the history, the sort of past and future of that wave is as it moves up and down. All right, so let's take a look at how we can sort of predict what a history or a snapshot graph could look like. Let's say we have just a wave pulse. Here is, I'm going to draw a little triangle wave. So this is just one pulse of a wave. It's got an amplitude up here, that is its maximum point, and it sort of increases linearly from that base point. That doesn't super matter, but this is what our wave is going to look like. We're going to say the wave is moving to the right with velocity v, and we want to know what is the history of a point P as the wave pulse moves into it. So essentially, you're going to watch how this wave travels into point P, and you're going to make a diagram of what point P sees as the wave moves into it. So here's our history graph. No, it's going to take some time for the wave to reach point P. So I'm going to start my graph out at 0. Then the first thing that's going to hit it is this large part. So it's going to jump straight up first. No, this is Y, this is T. And it's going to decay linearly from that point as the wave moves through it. Eventually the wave is completely passed through point P, and we have a flat line once again. So you might be asking yourself, why do we draw the triangle backwards? It's really sort of, we have to think that V is moving to the right. The first thing that's the point P is going to see is the largest amplitude. So the way I like to think about this is, imagine you had a train with 3 carts in it. So from left to right, we're going to label these carts A, B, and C. And this train, just like our wave pulse above, is going to move to the right. As it moves to a point ahead, as it crosses this sort of gate, what we see is that in order, as the train moves through this, you're going to hit train cart C first, B is going to come next, and then A will follow after that. So even though we have A, B, C from left to right, as the train moves to the right, C hits the point first. That's the first thing that we see, so that's what we draw first in our history graph. B follows next, and A comes in order. So if you have a wave pulse traveling to the right, you sort of want to flip it around as it hits that point in succession. So now, if this wave were going to the left, I guess point Q would be over here now. We want to draw the history of point Q. Now we would draw the wave in the same order because the smaller part is going to hit Q first and go in that order. Not to scale. So, sort of, if the wave is moving to the left, moves to left, the wave preserves its shape. And if it moves to the right, the waves flip around as they're drawn. So just like the train, we drew it A, B, and C. C, if it's moving to the right, is going to hit the gate first, and that's what we draw in terms of history chronologically in time. All right. We've talked about how to represent waves. Our next step is going to be, sort of the anatomy of a wave. What structure does it have? So to do this, let's take a look at both a history and a snapshot graph, because you can get different elements of the wave from each of these graphs. So here is our history graph. Here is our snapshot graph. If I have a wave that's measured in time, the characteristic dimension along this horizontal axis is our period. Just like with the pendulum, the time for one cycle is known as the period. We can also define the amplitude A, again measured from equilibrium up to the top of the wave, or likewise from equilibrium down to the bottom of the wave. So our amplitude just is the same as before. When we get to our snapshot graph, the horizontal dimension is no longer the period, as it has to have dimensions of length, and instead we call this the wavelength. This funny symbol here is lambda. It looks like an upside down Y. If you're familiar with the Half-Life video games, you'll know this symbol well, but it is called lambda. And that represents the wavelength of the wave. So again, the period is the time for one cycle. The wavelength is the distance the wave moves in one cycle. The amplitude of our snapshot graph is still A. So both kinds of graphs have the same amplitude. So amplitude is same for both graphs. Period is related to frequency by 1 over f. So we can get how many times that wave moves up and down by taking the inverse or reciprocal of that period from the graph. The frequency f is again number of cycles per second. The wavelength has analogous quality. This k from our equation is actually equal to 2 pi over the wavelength. This is called the wave number, and it's just sort of a way to convert the wavelength of the system into units of radians. That 2 pi there gets us into radians so that we can actually put it into our sine function as before. So this is our anatomy of a wave. We have sort of its horizontal distance in time is the period. We have the horizontal distance in space as our wavelength, and both kinds of waves share the same amplitude. Just because we're looking at a snapshot versus a history graph doesn't mean it can randomly get taller or shorter than it was before. All right, so let's think about, we've talked about how a wave moves. So let's look at the velocity of a wave. Any old velocity is, the amount of distance traveled in time. So velocity in general is the amount of distance per the amount of time. If we specialize this formula to a wave, we have the special distance for a wave, which is our wavelength. And if we specialize the time, we get the period. So basically, the wavelength is the amount of distance traveled by the wave in one time period. If we recall that 1 over t is equal to the frequency, we get this very important formula that the velocity of the wave is equal to the wavelength times the frequency. And we can see that as, for a constant speed wave, as one of these goes up, the other one has to go down to balance that. So frequency and wavelength are inversely proportional. Mathematically, if we have our function a sine omega t minus kx, we can recall that lambda is equal to 2 pi over omega, and we can recall that k is 2 pi over, I messed up, I'm sorry, k is 2 pi over lambda, and our omega is 2 pi over the period. So in other words, if we go back to this velocity formula here, lambda over t, we can substitute in lambda as 2 pi over k and t as 2 pi over omega. What happens now is the 2 pi's cancel out, the omega flips up top to the numerator, and we get that velocity is omega over k. So if we have a formula describing what a wave is doing in time and space, we can just use the coefficients of t and x omega, and k respectively, and calculate the wave velocity from the formula by omega over k. All right, thanks for bearing with me so far. We got one last thing to talk about, and that is how a wave moves It's a terrible title. Let's go wave motion instead. That's much more exciting, or correct even. So we have wave motion. We can categorize waves by how they move. And there are two main categorizations. The first one is a transverse wave. A transverse wave moves by having, the oscillations be perpendicular with the velocity. So if the wave moves one way, say to the left, then the oscillations have to be perpendicular to that, say up and down. So it might move a little like this. So if we were to draw this, we have, just as you saw, we have, the wave might move that way, V, and the oscillations go up and down. I like to think of a transverse wave as it has a lot of S's in it. So we have one S here, we have another S here, and this wave snakes up and down just like an S might. So you can remember transverse because it moves like an S. So that is contrasted with a longitudinal wave, which moves, oscillates parallel to direction of motion. So if we were to visualize that kind of wave, it would look a little like this. A longitudinal wave moves in and out like an accordion. So I like to think that it moves along the direction it oscillates. We can sort of draw this like, so we're going to visualize what a sound wave actually does. So a longitudinal wave, a sound wave is a prime example of a longitudinal wave. So what happens is we have alternating regions of high air density and low air density as that wave propagates through the air. So we might have places where the air is really spread out, but it gets closer and closer and closer, and then spreads out once again, and then contracts in on itself. So we kind of have these alternating places where the pressure presses in, out, out. So we have in, out, in, make it real dense, out. And so the wave moves along this direction, but the actual oscillations have alternating periods of high and low density as it compresses in and out. All right, so that does it with our introduction to waves. Thanks for cooperating with these trying times. We hope you were able to learn something, and have a great day.